last lecture we completed revision of fluid mechanics, so we'll continue with properties of matter today. And let's look at the concept of stress and strain. Concept of Hooke's law. So as you know that when the material is in the elastic region, stress is directly proportional to strain for any material, such that the amount of stress is within what we call the proportionality limit. And in that case, it is also within what we call the elastic limit. That is, the material behaves elastically. So we're looking at the property of elasticity here. Which means that the material will retain or have a tendency to retain its original shape. So when we look at stress versus strain as a relationship, so the amount of stress applied versus the amount of strain. See that the initial part of the graph is linear up to a certain limit, which is called the proportionality limit. After that, the stress starts to increase disproportionately with respect to the amount of strain. So that is called the elastic limit. Now, beyond the elastic limit, what happens is that the material becomes what is called plastic. That means up to the elastic limit, if I increase the stress, the strain will increase. But if I decrease the stress, it will also return back and come back to natural shape. That happens up to elastic limit. But the moment we cross the elastic limit, there is permanent deformity. So if we come somewhere here, and now we release the stress, the body will have some amount of permanent deformity. Okay. And of course, there is some point called the yield point, at which what happens that even a slight amount of stress causes the body to change in shape very drastically before it finally breaks. And that is called the breaking limit. Okay. So there is the proportionality limit. There is the elastic limit. Then there is the yield point. And finally, there is the breaking stress, where the body actually fractures. So for stress greater than the elastic limit, given material will lose its property of elasticity. That is the property to retain its original shape when stress is released. That property is called elasticity. So it will lose its property of elasticity and display the sort of counter property which is called plasticity. Plasticity is the property whereby your body is permanently deformed. Of course, our concern is more with Hooke's law. And Hooke's law, as we have seen, is that stress is directly proportional to strain. So that is the modulus of elasticity. For stress being within the proportionality limit. So the numerical part of this chapter is completely based on this. However, you should know the definition of the other terms like proportionality limit, elastic limit, the concept of plasticity, etc. These things you should just know from a theoretical point of view. So for example, we have longitudinal stress upon longitudinal strain is a property which is called Young's modulus. Then we have shearing stress upon shearing strain, which is the property called the modulus of rigidity. Right? So longitudinal stress क्या होता है? It is the change in longitudinal dimension divided by the original dimension. So longitudinal strain. Longitudinal stress क्या होता है? It is tension per unit cross sectional area. And strain is fractional change in the longitudinal dimension. Similarly, shearing stress is what? It is tangential force per unit area at a cross section, and shear is the amount by which the body gets bent, and that is the modulus of rigidity. And similarly, you have the third property of bulk's modulus, where it is volume stress and volume strains ratio. That is the bulk's modulus. So volume stress is nothing but pressure on the surface of a body, and volume strain is, of course, in all of these, there is always a magnitude amount. So whether the change is positive or negative, we take it as the magnitude. Okay. So let us look at the concept of longitudinal stress and strain. So if this, let's say, is the natural length of a longitudinal material which has cross-sectional area, then subjecting it to external force like this will create an internal tension at every point, where that tension will be equal to F in this case, and the body gets elongated. So it experiences a tensile or longitudinal stress of E by A, which in this case becomes F by A, and a corresponding longitudinal strain of delta L by L, and the ratio of stress upon strain is the material property, which is called Young's modulus. So the more important thing here is that you can see that the amount of tension developed is directly proportional to the amount of elongation. It is equal to Ey by L times delta L. And we also do a calculation of the elastic potential energy stored, that will come out to be this one. This is the work done by the external agent. This elastic potential energy that will be equal to the work done by an external agent to strain the body by the amount delta L by. Now, if you look at both these expressions, you realize that you can develop an analogy. Okay. It's analogous to the action of a spring. Where tension or the spring force is kx in magnitude, and the potential energy stored in the spring is half kx. So comparing these equations, you can see that a longitudinal material of natural length L, area of cross section E, and Young's modulus Y is equivalent to a spring, or it has an equivalent spring constant of K equal to Ay by L. So this is the formula that becomes very important to focus on at the numerical level, especially for JEE type of problems, where there are combination of materials, etc. We always use this. Okay. So the equivalent spring constant for this kind of a body, which has area A, length L, and the material is made of Young's modulus Y. I mean, the material property of the body is Young's modulus Y. It is equivalent to a spring, an ideal spring like this, where the spring constant will become this much. Okay. So let's see a couple of questions based on this, because this is an important thing numerically. So for example, we have a situation like this now. We have this. So this is a metallic rod, which has, let's say, natural length 2 meters, area of cross section 4 centimeters square. It's made of material of Young's modulus 9 into 10 raised power 10 Newton per meter square. Okay. Typically, Young's modulus of metals has an order of magnitude of 10 raised by 10. This is another metallic rod of natural length, let us say 3 meters. Area of cross section, let's say 5 centimeters square, and is made of material of Young's modulus, let us say 6 into 10 raised power 10 Newton per meter square. Okay. Now, what we are going to do is an external horizontal force will be applied like this. Okay. So, an external horizontal force F is applied as shown. So find the stress and strain in each rod and the force F. If it is found that the junction point that one displaces by 1 centimeter on application of the force F. So this is the question. Just try this out. So this is the junction point over here. So that junction point apparently moves by 1 centimeter when we apply this force. So based on that, we have to find the amount of force that we are applying, as well as the stress and strain developed in each of these. Okay, people, so just try out this question. Okay, so hope you worked out the question, people. So this is a simple situation where this combination that you have, okay, it can be replaced with an equivalent combination of springs. You will see. Just a moment. So this can be treated like an equivalent combination of springs. So this whole arrangement that we have, this is equivalent to something like this, where this is rod 2, this is rod 1. So this has an equivalent spring constant. And then we are going to apply the force from this side. So when we apply the force like this thing's length will become L1 minus X1. And this thing's length will become L2 minus X2. And they will have a common amount of tension. So that tension will be equal to F, and that tension will be equal to K1 X1, which will be equal to K2 X2. So K1 is E1 by 1 by L1. So that was 4 centimeters square minus 4 into Young's modulus. 4 centimeters square, 9 into 10 raised by 10 and 2 meters. This is 1.8 into 10 raised power 7 Newton per meter. And similarly, K2 is E2 Y2 by L2. That was 5 centimeters square, 6 into 10 raised by 10 and 3. This is 1 into 10 raised by 7. So you can see that X2 is equal to 1 centimeter, because that is the displacement of the junction, an application of the force. So K1 X1 is equal to K2 X2 is equal to F. So F will have to be 10 raised by 5 newtons, and X1 will become 1 upon 1.8 centimeters. Or behind this. the concept is clear in this question. So you can see when you apply this force, because this is a rigid wall, so this junction point moves by the amount which is equal to the compression in this spring, x2. Whereas the point of application moves by x1 plus x2. So I'll just leave you to the calculation part of this moment. Okay. So hope this is people. This is clear, people. So as far as the amount of force is concerned, that is so much. And from the force, you can calculate the stress in each of the rods. So the stress in rod 1 will become F upon A1. The stress in rod 2 will become F upon A2. And the strains will be X1 upon L1, X2 upon L2. And X1 and X2, X1 is equal to this much, whereas X2 was given to us 1 centimeter. Okay. Let's move on to another example. So in this next example, what we have is sort of coaxial kind of cylinder. So the cross section of the cylinder, that looks like this. So this part is made of, let us say, steel, and the inner core is made of, let us say, copper. So it's a coaxial metallic cylinder which has common length L. The inner core made of copper has radius R, and the outer shell kind of thing made of steel has radius, outer radius equal to 3 R. So now if this thing is to be stretched out to this dimension, find the amount of force needed in terms of LR and Young's modulus of copper and Young's modulus of steel. This is the next example. Okay, people. So in this example, what we'll understand is that when we are applying the external force, this combination of materials, what is happening is so this force that we are applying from the both the sides, it's going to create tension in the outer sheet, like this, as well as tension in the inner core. So the amount of force we are applying in this case will be equal to T1 plus, and T1 will be E1 by 1 by L1. L is common actually for both of them. Delta L plus because this whole thing will get compressed by delta. So this is like a case where the force we are applying is K1 is plus K2x. K1 plus K2 intervals. It is like a parallel combination of strings. That's what's happening here also. So this will be pi into 3r squared minus r squared into Young's modulus of steel divided by L plus pi r squared into Young's modulus of copper divided by L. This will be the relationship between the amount of force we are applying and the amount of compression the system will experience. So you can see that this area is A1 and the inner shaded part, that area is E2 for the compound. So hope this solution is also clear to all of you. I'll just leave you to understand this for a moment before we continue with the next problem. Okay, people. So let's move on to the next section. Where we understand variable stress and strain. Non-uniform. So the application of integration comes in. So for example, there is a situation like this. So on a smooth surface, we kept a combination of two blocks of mass capital M each. Let's say there's a metallic rod joining them, which itself has a mass small m, a natural length L, area of cross section E, and it is made of material of Young's modulus Y. So now let's say we apply an external force F like this, and as a result of that, the system is accelerating. The whole system starts accelerating with E. Yes, but also while it is accelerating, the rod is stretched out because of its elasticity. So given that capital M is equal to 5 times small m, is equal to, let us say, 10 kilograms. And the force we are applying is 220 newtons. And the area of cross section of the rod, mass 2 kg, area of cross section 4 centimeters square. Natural length equal to 2 meters. And it's made of material of Young's modulus 9 into 10 raised power 9 Newton per meter square. So we want to find the extension in the rod. Just try and work this out, people. Okay, so let us work out this particular question. So people, what happens in this kind of situation? As you can see that the system will have a common acceleration. Which we calculate by taking the combined free body diagram. We take this whole thing as a single FPD and consider the horizontal force on it. So it has an acceleration of this much now. The combined acceleration is this. So that becomes 220 newtons divided by the total mass, which will become 2 into 10 for the 2 blocks plus 2 kg for the rod. So 10 meters per second square is the combined acceleration. Now you see the situation of the rod. Now the situation of the rod is such that it's having an acceleration E because of some tension T1 at this end and T2 at this end. And further, you can see the block on this side. It's having T2 and the block on this side. It's having T1 and F. The same acceleration. So you can see that T1 will come out to be F minus T2 will come out to be M. But the more important thing is that within the rod, if we take a point P, which is at a distance X, let's say over here, then how much is the tension? It's non-uniform. As a function of X at a point P. So how do we calculate that? So for that, what we do is we make an FPD of this section of the rod. It is of length X. This tension is T. This T2. This is having an acceleration. So T minus T2 is mass of that much section into the acceleration. So P becomes T2 plus small m by L X. So this equation tells us that tension as a function of X. It is becoming capital M plus m by L X, or becoming m plus mx by L into E. So you can see that it is or numerically tension is equal to 10 plus x by L into this acceleration, which was this is the tension in newtons. This is the expression for tension. So next, what do we do when we have a variable tension like this? We take a differential element within the rod and we apply stress and strain concept to that. So for that rod now, at that distance x, we consider a differential element, and because of the stress the rod is under as it is accelerating, so the entire length of the rod is elongated by delta L, which means that each sectional element is also elongated. This is like some dx plus some small change in dx. So that section, that differential section, it had a natural length of dx. So it has an elongated length of dx plus, it's a small delta of x. So it has a strain of this much. So that strain is equal to Young's modulus into stress, or rather stress divided by Young's modulus. So that is P divided by. So the elongation of that section, and this we had just seen was this. Like this. So that elongation, this whole constant, into dx. So now we can find delta L as the integrated sum of this delta x. That is integration of this whole quantity. Integrated from x equal to 0 to x equal to 1. So next step, to take all the constants outside. Carry out this integration, so that is so you will get a quantity like this. Then you can substitute them. That will become 220 newtons divided by the mass total, which was this much, into 10 plus 1 here, divided by the area of cross section, which was 4 centimeters squared, into the length we had taken as 2 meters, and the Young's modulus was 9 into 10 j square 9. So this will become the amount of extension in meters, which will come out to be a small quantity in millimeters. Anyway, so this is the important concept of variable stress. Coming from the fact that the tension itself is non-uniform. So first find tension as a function of x. Then you apply the concept of stress and strain to a differential element, done next, and then integrate the strain to get the entire strain on the entire material. I made works. So this is the concept of variable stress and strain applied over here. Okay, let's move on to an example of shearing stress and strain. So in this next example, what's happening is that we have a block whose this area is, let us say, 2 meters square. And it's lying on a rough surface of coefficient of friction equal to, let us say, 0.2. And on top of that, there's another block which is lying. This has a mass m1, this has a mass m2, and this height is h. And we start applying a force like this. So given, suppose m1 is 2 kilograms, m2 is 3 kilograms. G is 10 meters per second square. And the force we are applying is, let us say, 20 newtons. And that area there was 2 meters square. And the height of that thing is, let us say, 10 centimeters. Okay. So if the material of the lower block just a minute. This also has the same coefficient of friction. This is also 0.2. So if the material of the lower block, let's say rubber or something, has a modulus of rigidity theta of 6 into 10 raised power 6 Newton per meter square, find the shearing stress and strain on the rubber block, the lower one. Okay, so what you'll realize here is that application of this force will result in some kind of friction here, and that will result in some kind of friction here and some kind of friction here. So this is creating this friction, and this friction here is creating this kind of situation. It's creating a shear within the body. And that is going to cause this to bend. So the shearing strain is basically the amount of bending. So first of all, there's a Newton's laws friction kind of element in this, where you have to understand how much friction is acting on each of the surfaces by application of free body diagram and Newton's laws concepts. And then from that only you will be able to calculate the shearing stress, and then you will apply Hooke's law. Shearing stress upon shearing strain is equal to modulus of rigidity. So those are the concepts you'll have to apply in this question. Okay, so you'll realize here that M1 is equal to 2 kg, M2 is equal to 3 kg. And this force we were applying was 20 newtons. And the coefficient of friction in both places was 0.2. So now if we consider the frictional forces, this surface has F1 and this surface is F2. So we can see that F2's maximum possible value is mu into M1 plus M2G. So that is 0.2 into 2 plus 3 into 10. So that is 10 newtons. So since F is greater than F2 maximum, so the system will experience both the accelerations not zero. It2 will also not. Okay. So now, assuming common acceleration, that is E1 equal to E2 equal to E, or no slipping between the blocks, you can see that if you make a combined free body diagram, on that this force is acting. this limiting friction from the ground is acting. So E will be capital F minus F2 divided by M1 plus M2. So that will be capital F minus mu into M1 plus M2G upon M1 plus M2. So this common acceleration in that case should be equal to 20 newtons minus this was 10 newtons we calculated, whereas this was 2 plus 3 or 5. So 2 meters per second square. Okay. But we have to check the friction F1. So for that we can see that on this block, F minus F1. So 20 minus F1 should be equal to 2 into 2. So the amount of friction required here will become 16 newtons. Okay. Whereas F1's maximum possible value is mu M1G. So mu was again 0.2 and this is 2 into 10. So it is only 8 newtons. Sorry, 4 newtons. So this much friction is not available to us, which means that A1 will not be equal to A2. Okay. So this will not be possible. Okay. So that means there is slipping. And the lower block is at rest. So what happens in this particular case is that this is going to be mu M1G and this is going to accelerate. Whereas the lower block, इस पे ये जो फ्रिक्शन ऐड करेगा this will get absorbed by static friction because this will be at rest. So that static friction from the flow will be equal to the kinetic friction on this surface, which will be equal to mu M1G, which will be equal to 0.2 into so 4 newtons. Okay. So this is what is going to happen. So this is going to be the condition of the lower block now. The lower block will get bent slightly like this because of the friction acting. This is going to be the state of M2 because इस पे यहाँ पे ऐसा फ्रिक्शन लग रहा है. So this body has got sheared. It's got this ऐसा हो गया और it's got bent by theta. So the shearing stress is the tangential force divided by that area of cross section. So that here will be mu M1G divided by this area on top, this area, or this area below. Okay. And the shearing strain produced will be equal to theta, which is approximately x by h. And the ratio of shearing stress to shearing strain coefficient of rigidity. Straight theta or x by h. This quantity will be equal to mu m1g by theta. So that will be 4 newtons divided by coefficient of rigidity, which was this modulus of rigidity, into whatever area we are taking. 2 meters square. So this will give me this thing in radians, or that is approximately x by h. We want to find out how much that is shifted by that x. We can put this. So this is an example involving shearing stress and shearing strain. Actually, here, rather than this analysis, what is more important here is that F1's maximum value, which is mu m1g, is only 4 newtons, and F2's maximum value, which is mu m1 plus m2g, was equal to 10 newtons. So therefore, we can see that the lower block K2 will be at rest. The lower block does not move. So this is the most significant condition in this. Right? This will not move. So this assumption of common acceleration and all that is not required. You can directly come to the lower step. From this, we can see this, and from that, we can come to this. This situation, there is slipping. Okay, so this is the concept of Okay, so people, that's about shearing stress and strain. Now, next example we see is something to do with volume stress and strain. So, something like this. We have spherical sponge ball of radius r and made of material which has bulk's modulus. So this sponge has a bulk's modulus of elasticity. It's very elastic, soft kind of material. So its modulus of elasticity is less. So it has bulk's modulus, let's say 3 into 10 raised power 4 Newton per meter square. This is its bulk's modulus. Of elasticity. Let's say 10 raised power 6 rather than raised power 6 or even 10 raised power 7. Now, this ball is taken under water to a depth of 6 meters. Okay, so we want to find volume stress and volume strain that is under, and also we want to find the percentage change in the radius of the ball. Just try this out. It's a direct formula based question. You can see that the excess pressure that it will be under, that is going to be the hydrostatic pressure rho gh. So it's a direct application of that concept, hydrostatic pressure. Okay, so what's happening here is this sphere has a certain radius r when it is under atmospheric pressure. But the moment we take it underwater to a certain depth, take it underwater, so from its natural size, it shrinks. It is under compressional strain. Okay. So its volume here was 4 by 3 pi r cube. Here its volume becomes V minus delta V. That becomes 4 by 3 pi r minus delta r. So now for that volume strain, we use the Bulk's modulus and Hooke's law concept. That is volume stress upon volume strain ratio. That is equal to the Bulk's modulus. So underwater, the pressure it is going to be under here. If it is at a depth of h, so the pressure is changed to P naught plus delta P. So that is P naught plus rho gh. Okay. So it was at a depth of 6 meters underwater. Just a second, people. I have to reshare the whiteboard. Right. So the volume stress it undergoes, the material, will be this, and this is mod of delta V by V. So in this, the volume stress is the excess pressure. So that is rho gh. So for water in SI unit, the density is 1000 kg per meter cube. G will take as 10 and this is 6. So this is 6 into 10 raised power 4 pascals on Newton per meter square. That is the volume stress. And the Bulk's modulus we are taken as 3 into 10 raised power 7. Newton per meter square. So substituting this, we can see here the volume strain, that is delta V by V, becomes the volume stress divided by Bulk's modulus. So that in this case becomes 2 into 10 raised power minus 3. So as a percentage also you can see that delta V by V percentage be a 0.2% compression. Now the very important concept here, volume is directly proportional to radius cube. So apply the concept of percentage errors. So delta V by V is 3 times delta R by R for small fractional change. This is from the concept of propagation of error or binomial approximation. So delta R by R will be 1/3 of delta V by V. So the radius decreases by a factor of 0.067%. This is the final concept over here in this question. Okay, so I'll just take you through the whole solution once. So take it to a depth of h, it experiences hydrostatic pressure of rho GH. So the excess pressure which is creating the volume stress on the rubber sphere is rho GH. So accordingly we can calculate the volume strain by using the Hooke's law. Value of bulk's modulus of rubber is given to us. So that is giving us the volume stress and the volume strain finally, delta V by V. The compression is as a percentage, it is 0.2%. Then we are just using the concept of binomial approximation, or you can say it's a concept similar to error propagation. The relationship between volume and radius, it's a cubic proportionality. So as far as small changes is concerned, the radius will have a percentage change which is 1/3 the percentage change of volume. Okay. So that's how we get this final answer. Okay. All right, people. So that's it for today's session. With this, we complete the elasticity part of properties of matter. Okay. And next session, we will be moving on to the properties of fluids, that is surface tension and viscosity. With that, I think we'll finish this properties of matter revision section and we can decide on some next chapter after that. Okay, thanks for attending, and that's it for today's lecture. I'll send you the recording and the whiteboard notes. All the best.